The sun is the prime mover of life. Dominating the sky with its brilliant light, the sun has been integrated into virtually every myth and religious system that humans have ever developed. In some religions, like Hellenism, the sun is a chariot being driven by a deity across the sky. And in other religions, the sun either represents a deity or is literally believed to be a deity in its own right. Even when we strip the sun of all of its mythological baggage and analyze it solely through the secular lens of science, the sun arguably retains, at least thematically, its godlike reputation. Compared to a puny human life, the sun might as well be immortal. It flexes its immense power by fusing 600 million tons of hydrogen into helium every second. It is the giver and supporter of virtually all life on the planet, with the exception of chemotrophic microbes living in deep-sea vents. Life thrives here on Earth, but the reason that life can exist here in the first place is not just because of Earth's favorable composition, but also because of Earth's position relative to the sun, with all of its particular traits and attributes. The sun is a population 1 G2V type star. The G2 classification means that the sun has a white color spectrum, and it's on the warmer end of the G-type stars, with a surface temperature of about 5800 Kelvin, which is more than 5500 degrees Celsius, and close to 10,000 degrees Fahrenheit. The V classification means that the sun is a main sequence star. It's not a white dwarf, it's not a subgiant, and it's not a giant star. When compared to most other stars, the sun is relatively large and bright, but this is only because most other stars are white dwarves, red dwarves, and brown dwarves. These small, dim stars are numerous, while larger, hotter, brighter stars tend to be much less common, increasingly so the larger and brighter they are. All things considered, the sun is estimated to be larger and more luminous than about 85% of the stars in the galaxy. The sun is also unusually stable for its class, perhaps due to the fact that it isn't excessively large, and it isn't rapidly burning through its fuel. The population 1 designation means that the sun is unusually rich with metals. In astronomy, there's hydrogen, there's helium, and everything else is a metal. So elements like iron, sodium, magnesium, oxygen, neon, lithium, in astronomical terms, they're all metals, because they're all heavier than hydrogen and helium. Why is this the case? Why is the sun unusually metal-rich? It turns out this is because the sun is a relatively young star. It's only 4.6 billion years old. When the first stars came into being, way long ago in the early days of the universe, the only available atoms were hydrogen and helium. These first stars had the mass and the energy to fuse these two base atoms into heavier atoms. And when these first stars died, the heavier atoms that they created were dispersed into the interstellar medium. Newer generations of stars were formed out of the accretion of this interstellar medium, and because it now contains a wide variety of metals, the newer generations of stars necessarily were composed of more metals too. So if you let this process continue for about 9 billion years, with each generation of stars being more metal-rich and producing more metals upon their death, eventually you get a pretty metal-rich interstellar medium. By the time the sun formed, the stuff that was accreting to make the sun had a high proportion of elements that were heavier than hydrogen and helium. Our entire star system was formed out of the same accreting mass of interstellar medium, and the high metal content made it more likely for planets like Jupiter to form. Counterintuitively, rocky planets seem to exist around most stars, but it's only the metal-rich stars that seem to consistently host gas giants. This observed trend suggests that a high metallicity is important in the genesis and the development of gas giants. Alright, so virtually every star is surrounded by a region called the habitable zone. This is what I really want to get into today, because this is most likely going to be the prime determiner of life in a given solar system. I say most likely because it's not guaranteed. Life isn't completely restricted to a clearly defined habitable zone, and as this episode goes on, hopefully that'll be made clear to you. This habitable zone is an area around the star where the temperature is just right, and assuming that an orbiting planet has sufficient atmospheric pressure, liquid water could theoretically exist on its surface. A planet that orbits beyond the habitable zone receives too little light energy from its star, and it's unlikely to have liquid water. Because it's far from its star and it's not receiving that much energy, it's going to be relatively cold, and any water that exists on such a world would be frozen into ice. Conversely, any rocky planet that orbits in the hot space between the star and the habitable zone itself would receive too much light energy, and any liquid water would boil away into vapor, floating into the atmosphere where UV radiation could break it down into free oxygen and molecular hydrogen. Now, the habitable zone, where liquid water can be sustained on a planetary surface, is a critically important variable for potential life in any given star system. Before I go any further, I want to clarify something. You might think that habitable zones are easy to calculate, that they have crisp borders delineating where liquid water can and can't exist, and that any planets outside the habitable zone have zero chance for hosting life. This is not the case. Habitable zones are really complicated, and there's countless variables that can influence whether or not a planet develops life. If you came into this episode with the preconception that habitable zones are clean and simple, I hope you will be disabused of that notion by the end. First and foremost, it should be obvious that the habitable zone varies in size from star to star. A smaller, cooler star, like a red dwarf or a white dwarf type star, will have a smaller, closer habitable zone, while larger, hotter stars, like an A-type or a K-type giant star, will have wider habitable zones that are positioned farther out. The Earth sits comfortably within the middle of our Sun's habitable zone, perhaps a little closer to the warmer edge. Although the habitable zone is more like a gradient between higher temperatures and higher sunlight at the near edge and lower temperatures and lower sunlight at the far edge. The Earth orbits at 1 astronomical unit, or 1 AU, away from the Sun. This is about 93 million miles, or 150 million kilometers. The Sun itself, being a mid-sized star, has a habitable zone that begins at about 0.7 AU away and extends out to around 1.3 to 1.8 AU. This is really interesting, because Earth is not the only planet in our solar system that orbits within this roughly defined habitable zone. Venus at aphelion, or the point in its orbit where it's farthest from the Sun, will actually dip into the warmer edge of the habitable zone. However, Venus's atmosphere is extremely dense and choked with greenhouse gases, which have turned the surface into an oven that's hot enough to melt lead. Liquid water can't exist on Venus because it's simply way too hot, even at the farthest point in its orbit from the Sun. Although this does raise an interesting point. The habitable zone can only ever be roughly defined, because it depends not just on the traits of the star in question, it also depends on the planet itself. A terrestrial planet that carries a thick, greenhouse gas-rich atmosphere will be able to capture and retain more heat, and thus, these types of planets could potentially sustain a habitable surface environment with liquid water even if the planet orbits on or beyond the cold edge of the habitable zone. If Venus had the same atmosphere, but it orbited our Sun at 1.6 AU instead of 0.72 AU as it currently does, Venus would probably turn into a warm, wet world. Conversely, the estimates of our Sun's habitable zone suggest that it extends out past the orbit of Mars, which means that Mars is technically within the habitable zone. It's just that Mars has so little atmospheric pressure that liquid water can't be sustained. When it gets warm enough, water ice immediately sublimates into water vapor. It's hypothesized that Mars can only host liquid water in its lowest elevation areas, where the atmospheric pressure is the highest, and even then, it can only do this briefly, during the warmest weeks of summer. At every other point in the year, and at every other point on Mars's surface, Mars is too cold and lacks the atmospheric pressure to sustain liquid water, even if it is, technically, within the habitable zone. Other types of planets can also blur the edges of the habitable zone. So-called desert planets, or dry planets with very little water, actually enjoy a wider habitable zone than other planets because of this lack of water. It's pretty counterintuitive, but water vapor is a greenhouse gas, and if you have less water vapor in the atmosphere, as you would on a dry desert planet, then the atmosphere is less able to hold onto heat. What this means is that a dry desert planet can actually be closer to its host star while still being able to retain some liquid water on its surface, like small lakes or oases. It's unlikely that a desert planet would have giant globe-spanning oceans. In addition, a lack of water directly implies a lack of ice. Ice is reflective and helps to cool a planet down, so a lack of ice means that the planet will absorb relatively more heat. This means that a desert planet can absorb enough heat to keep itself warm even on the cooler edge of the habitable zone. So a desert planet effectively has a broader habitable zone than the other planets in the same system, orbiting the same star. Alright, so the habitable zone depends on the temperature, size, and luminosity of the host star, but it also depends on the atmospheric and chemical qualities of the planet in question. As if this wasn't complicated enough, we must also consider the maturation and aging processes of the star itself, because this will change the size and distance of the habitable zone throughout the star's life. So a star is born when it accumulates enough mass, where the internal heat and pressure and density get so high that it ignites nuclear fusion in the star's core. As the star ages, this fusion activity will gradually increase. Our star, for example, was smaller, cooler, and dimmer in its younger days than it is now. During the Archean eon, some 2.5 to 4 billion years ago, the Sun had only 70 to 75% of its current luminosity, and as the Sun continues to age billions of years into the future, it will continue to get brighter. In a nutshell, this means that as a star on the main sequence ages, its habitable zone will slowly expand and get further and further out. As it ages, the main sequence star will expand. It'll get larger. Its core will begin to fuse helium atoms, and a massive mantle layer of hydrogen will expand outwards. This particular fate, where the star expands and sheds its outer layers of hydrogen, will happen to our Sun. As our Sun will age and expand, it will physically consume Mercury, and then Venus. They'll be incinerated and fed into the greater mass of the Sun. I think there's some debate as to whether or not the expanding Sun will eventually consume the Earth as well, but there's little doubt that the expanding Sun will, at the very least, burn the Earth to a crisp, boiling away all of its water and ending its capacity to host life. But as the Sun expands, it will also cool down, so the expanding habitable zone will expand proportionately slower than the star itself. I want to shift gears for a moment and look at the habitable zones and the potential for life around other types of stars. Different star types have different attributes, like lifespan, temperature, radioactivity, luminosity, stability, and so on. All of these things will influence the habitable zone and the likelihood that life might arise on a planet orbiting the star. So let's start small with the dwarves. The coldest, dimmest protostars are categorized in decreasing order under spectral type L, type T, and type Y. The type Y stars are tiny, cold brown dwarfs, probably heavy with ammonia, with surface temperatures that are measured in hundreds of degrees Kelvin. This might sound like a lot, but it's not. It's actually really cold as far as stars are concerned. It's about the temperature of a boiling pot of water. The coldest type Y star is only 250 Kelvin, which is actually colder than the freezing point of water. And these stars are like this because they're, as I said, probably heavy with ammonia. Needless to say, these stars are far too cold to even have a habitable zone. Class T and Class L brown dwarves are slightly larger and slightly hotter. The Class T dwarves are methane-rich, and the Class L dwarves are rich in alkali metals. But both of these types of dwarf stars are still far too small and far too cold to really have any kind of meaningful habitable zone. I mean, only the largest Class L dwarves are even capable of engaging in hydrogen fusion, which is technically the criteria for being called a star. The smaller Class L dwarves and the Class T and the Class Y stars are not really stars. They're just giant gas giants that are really cold. Class M stars are the red dwarf stars. Now we're starting to get into actual star territory, where they're bright and hot. These Class M stars are much larger and much hotter than Class L, T, and Y stars. And the Class M stars are relatively common, accounting for about 75% of all main sequence stars. But despite their abundance, they're still relatively tiny, dim, and cool, especially when compared to stars like our Sun. There's been a lot of research on the habitability of Class M systems, but the evidence has gone in both directions. One of the biggest problems is that because red dwarfs are small and cool, their habitable zones are narrow and close up. They're so close up that rocky planets in the habitable zone tend to be tidally locked. When a planet is tidally locked, one side of the planet always faces the star and the other side always faces away. The side that always faces the star gets perpetually blasted by heat and radiation, while the far side of the planet, the side that faces away into the darkness, is frozen in perpetual night. The initial thinking was that tidally locked planets are completely inhospitable to life, but recent studies have found that these planets might have weather patterns that create extensive cloud cover over their sun-facing sides. This cloud cover would help to cool the sun-facing side and trap heat in the atmosphere, which could help warm up the colder far side of the planet. This would allow for some kind of semi-stable atmosphere that could move heat around the planet and keep things from getting too hot or too cold. The atmosphere could moderate the planet's temperature. If there was liquid water, then this could moderate the temperature even more. Another variable is radiation. These smaller red dwarf stars are kind of unstable. They exhibit fluctuations in their luminosity and radiation output that can be hugely disruptive of life on a local planet. A sudden burst of luminosity could burn away life on a planet, and a sudden drop in luminosity could freeze life on a planet. Sudden bursts of radiation could sterilize its surface. In all of these cases, the planet's ecological stability is disrupted, and any native life could be quickly extinguished. These unpredictable fluctuations in luminosity could pose a serious long-term risk to any native life. But the radiation spikes, like sudden bursts of UV or X-ray radiation, might not be as dangerous as initially thought. A recent study found that even a thin atmosphere could offer enough protection from radiation to keep life alive. Now, personally, I think that life is definitely possible on planets orbiting a red dwarf star, but it would not be like Earth life. I mean, it could theoretically be carbon-based, it most likely would be carbon-based, but alien vegetation might be black instead of green, to absorb the red dwarf's light and to protect the tissue from UV radiation. If the light is too intense, then the plants might be white or some kind of pale color to reflect as much light as possible to protect them from being burned. Also, red dwarf stars have extremely long lifespans, measured in hundreds of billions, if not trillions of years. If life could theoretically appear and persist on a planet orbiting a stable red dwarf, it has many, many billions of years to look forward to evolve and diverge. Life could emerge, diversify, get wiped out by an asteroid or a supervolcano, then re-emerge, diversify, and get wiped out again, over and over again, for eons. The red dwarf star isn't going anywhere. It's not going to die for billions and billions and billions of years, and it's not going to expand and consume its planets. The star's brightness might fluctuate a bit, but the planets themselves are there to stay for the long haul. Going up the scale, we come to the Class K stars, which are larger, brighter, and hotter than the Class M red dwarfs. Class K stars are a broad and varied group, including subdwarfs, main sequence stars, subgiants, and giant stars. The things that unify them are their orangish color, their limited amounts of hydrogen, and, most excitingly, their relative stability. Where red dwarf stars exhibit luminosity fluctuations and occasional bursts of UV or X-ray radiation, the K-type stars are nice, peaceful, and stable. They emit less UV radiation than G-type stars like our Sun. They have a main sequence lifespan measured in multiple tens of billions of years, whereas our Sun has a lifespan of about 10 billion years. The K-type stars are also much warmer than M-class stars, with much broader habitable zones. Because of the abundance, warmth, stability, and long lifespan of K-type stars, they are considered optimal places to look for life. It's actually quite possible that K-type stars are more likely to host habitable planets filled with life than G-type stars like our own Sun are. This is kind of counterintuitive, but G-type stars are, believe it or not, actually kind of unstable. These yellowish stars include stars on the main sequence, as well as subdwarfs, subgiants, and giant stars. The main sequence G-type stars, like our Sun, have short lifespans compared to the K-type stars. Over the course of about 10 billion years, they'll expand into a red giant, shed their outer layers into the interstellar medium to create a nebula, and the leftover core material will condense into a super tiny, super dense white dwarf. This process, over 10 to 15 billion years give or take, will see the formation of the star system, followed by a brief window of stability where life can evolve, and then that window will be closed as the star ages, expands, and settles down as a white dwarf. Despite this window for life to emerge and evolve being relatively brief, measured in single-digit billions of years, this is more than enough time for complex life to evolve. G-type stars that aren't on the main sequence, like giants, subgiants, and supergiants especially, are even less stable. They will rapidly diverge into either Type K or M red giants, or Type O or B blue giants. Alright, moving on, the next type of stars are the Type F stars. Type F stars are slightly larger than our Sun, and slightly hotter, but they're also a lot brighter, with an even shorter lifespan. A study from 2014 found that if there was a terrestrial planet like the Earth, situated the same distance away from an F-type star as Earth is from our Sun, it would be exposed to a lot more heat and a lot more ultraviolet radiation, something on the order of 2.5 to 7.1 times more UV radiation. This increased exposure to ultraviolet light could be hugely dangerous for life, as it would degrade and destabilize genetic molecules like DNA. Being larger and warmer, F-type stars have larger, broader habitable zones, so planets on the outer edge of the habitable zone would still be able to host liquid water, but they wouldn't be cooked by the heat or brutalized by heavy UV radiation. The Type A stars are even larger and hotter than Type F stars, and they have even shorter lifespans. These Type A stars are on the upper boundary of hosting habitable planets. While they generate a lot of heat and light, and thus they have a broad habitable zone, they just don't live that long. There's enough time for life to emerge and evolve, but if we're going by Earth life timescales, there's just not enough time in the Type A star's lifespan for this alien life to evolve higher complexity. These problems only compound themselves farther up the spectrum, with Type B and Type O stars. Both of these types of stars give off bluish-violet light. They're very bright, they consume their nuclear fuel extremely quickly, and they age rapidly and have very short lifespans, measured in hundreds of millions or even tens of millions of years. So, while life might appear on a planet orbiting an F-type star, or even an A-type star, it wouldn't really have the time to evolve that much. Life on a planet orbiting a Type B or a Type O star definitely wouldn't have time to evolve, if it even had enough time to emerge in the first place. Now here's a twist for you. In all of this talk about the habitable zone being the key spot for life in a given star system, I failed to mention that the habitable zone is not the only place that life can emerge or sustain itself. For example, here on Earth, we've recently discovered the deep biosphere, populated by simple organisms with extremely slow metabolisms that replicate on 10,000-year cycles, and that live and die on the scale of hundreds of thousands of years. It's theoretically possible that almost any planet with some kind of tectonic activity, with some kind of heat and nutrient cycling within its crust, could host deep biome life. Furthermore, if a planet was once habitable and developed life, but was ejected from its star system, or it exists in an orbit where it periodically enters and leaves the habitable zone, this deep biome could preserve life on the planet. When this planet re-enters the habitable zone, or if it was ejected but eventually gets captured by another star and brought back into the warm embrace of a solar orbit, the life in the deep biome could seep to the surface and seed it with life, which could then evolve more complexity and establish a macroscopic surface ecology. Another potential avenue for life to exist outside of the traditional habitable zone is if this life is based on an alternative biochemistry. It's been hypothesized that on cold moons and planets, methane could be a suitable alternative solvent to water. A carbon, nitrogen, and ammonia-dependent biochemistry could theoretically exist in the lakes and rivers and oceans of methane that exist on the moon Titan. Planets and moons and other star systems could have life based on this kind of cold-tolerant biochemistry, but it doesn't end here. There's a wide range of theoretical biochemistries that could populate exotic alien planets. Silicon-based life is often proposed, but I'm personally skeptical of a purely silicon-based life form, as even though silicon has 4 valence electrons like carbon, it simply doesn't have the same chemical fertility as carbon. I think the most likely alternative silicate-based biochemistry that's remotely plausible is some kind of carbon-based life that just heavily integrates silicon. And because of this, the alien organisms secrete crystals or crystalline structures of some kind, instead of flat protrusions made of keratin or chitin. Or maybe silicon, when integrated on a biochemical level, creates some kind of strange, soft tissue with novel properties that we wouldn't expect from some kind of biological organism. Now, the prime example of life outside of the habitable zone is the stereotypical moon of a gas giant, with its icy crust and subsurface liquid water ocean. The subsurface ocean can be heated in several ways. Tidal forces from the host gas giant pulling and warping the core and the crust can generate heat, as can any potential tectonic and volcanic activity. Radioactive materials in the core can also create heat through their decay processes. This heat can supply raw energy into the subsurface oceanic ecosystem, potentially supporting a complex alien ecology. My favorite aspect of these potential subsurface alien ocean ecologies is that they would exist in complete darkness, as the ice shell would block out all incoming light from the sun and the stars in the night sky. If these alien fish analogs ever evolved some kind of visual system, it would be to detect the biofluorescence of their prey and/or predators. These life-bearing moons, far out of the habitable zone, could, at the extreme end of the badass spectrum, be populated by complex, glowing alien fauna, like the monstrous octopus creature depicted at the end of the movie Europa Report. So, the habitable zone is not a clean boundary delineating where life is and is not possible. The habitable zone is a rough transitionary boundary. It's a temperature gradient, and while it's mostly defined by the traits and qualities of the star, the chemical and physical composition of the planet also plays an immense role. And while the habitable zone is a guide to where liquid water might exist, it's not a hard boundary. We know that liquid water can exist beyond the habitable zone, under the ice sheets of frozen moons. I suppose the question is, what's to be made of this? How will this knowledge influence our search for life out there in the cosmos? Honestly, I think we're still in a really early stage in our observations of other star systems. In very recent years, our discoveries of exoplanets and our growing understanding of planetary and star system formation have radically increased, and this portrays a universe that is much more planet-rich than we once thought, several decades ago. The habitable zone remains the most obvious, straightforward place to look for life. To date, we've found numerous exoplanets orbiting in the habitable zone of their star. Some of the most promising among them include TRAPPIST-1e and G, which both orbit closely around a red dwarf star some 39 light-years away. There's Gliese 667c sub c, orbiting a red dwarf star some 24 light-years away. There's Captain B, orbiting a red dwarf star about 13 light-years away. And most excitingly, Proxima Centauri b, which orbits the red dwarf star in the nearest star system to Earth, some 4.2 light-years away. It's a curious fact that the majority of these known exoplanets orbiting in the habitable zones of their stars have these snug little orbits around a red dwarf star. Is this a trend across the galaxy? Is there something about G-class stars that makes them relatively less likely to have terrestrial planets? What about gas giants with moons? What about the moons of a gas giant that orbits in the habitable zone? Instead of ice-encased ocean moons, would we instead see temperate moons with liquid water and a warm, comfortable climate rich with life? If we identified a large quantity of molecular oxygen in the atmosphere of an exoplanet, what does this say about potential life? I don't have the answers to these questions. To figure out these mysteries, and to learn more about the galaxy and the universe in which we live, we have to keep looking up and studying the night sky with the same passion and wonder as our earliest hominid ancestors.